Welcome everyone. Thanks for joining this. Today I am going to speak about a topic which is getting serious attention in India and globally, that is small modular reactor or SMRs. More specifically, I will talk about the Bharat Small Modular Reactor BSMR and how it fits in India's future nuclear power roadmap. Before I begin, let me say one thing clearly. This talk is meant for any engineering professional of all domains: mechanical, electrical, civil, instrumentation, chemical, even IT and project management, not only for nuclear engineers or nuclear scientists, because nuclear power projects are not just about reactors. They are large multi-engineering systems, so they need pressure vessel fabrication, high capacity pumps, precision instrumentation, electrical distribution, control system, civil construction, quality assurance, safety design, discipline, project execution. So this topic actually touches many engineering disciplines. I will structure this talk in a simple way. पहले हम लोग क्या करेंगे, we will cover main reactor types, why people compare PHWR and PWR in the SMR discussion. Secondly, I will share the Indian current installed nuclear power and ongoing projects. Third, I will explain why SMRs are needed not as a replacement but as a support route to grow faster, especially for captive power, new industries and many other things. And finally, I will discuss about Bharat Small Modular Reactor 200, BSMR 200, what is the special about its design and what progress India has already made in key components and design. So why SMRs are being discussed now? Let's start with that questions. Not just continue building large reactors. Why we are not pursuing only with the large reactors? The main reason is scale and speed. India is aiming for major nuclear expansion, and the long-term vision discussed is to achieve 100 gigawatt electrical by 2047. This number is very large compared to where we are today. It requires steady construction, stable fuel supplies, strong manufacturing, most importantly practical deployment option. Also the demand profile of electricity in India is changing. Globally it is changing, and India it is going to change a lot. Today the grid is not the only story. We have sectors that want dedicated high reliable power. Captive power is one major driver. In Indian industries like steel, heavy manufacturing, stable electricity production is necessary. Any outgoing outage is not just a power issue, it becomes a process safety issue, power production quality issues and cost issues. Data centers are another major drivers. Data centers need power continuously, 24 hours a day, 7 days a week. Even short disturbances can cause operational issues. India already has a large number of data centers. That number will only rise with AI and digital growth. So SMRs are being discussed because they can provide reliable, firm, low carbon power. They can potentially be deployed faster and in more flexible locations compared to very large reactors. And from a national planning perspective, SMRs also support long-term energy security and reduce dependence on fossil fuel volatility. Let's have a quick overview, main reactor types. To understand BSMR, we first need to understand major reactor types in simple terms. PHWR, pressurized heavy water reactor. PHWR are the backbone of India's nuclear power program. India has extensive experience with PHWR design, construction, operation, maintenance, scale up. One major reason India adopted PHWR strongly is PHWR uses natural uranium effectively and can produce plutonium efficiently, which supports India's long-term nuclear fuel cycle roadmap. PWR are pressurized water reactor. These are light water reactor. PWRs are globally the most common power reactor types. The typical use of light water as coolant and moderator and enriched uranium fuel. Worldwide, PWR design philosophy is mature, well established and widely deployed. And BWR के बारे में बात करेंगे. It is boiling water reactor. BWR, boil water inside the reactor vessel. India has a historical experience in Tarapur, but future mainstream expansion is more focused on PHWR and PWR-based option only. FBR में क्या आता है, फास्ट ब्रीडर रिएक्टर. फास्ट ब्रीडर में इंडिया शुरू किया था फास्ट ब्रीडर टेस्ट रिएक्टर में. देन उसके बाद PFBR. फास्ट ब्रीडर रिएक्टर्स आर इंपॉर्टेंट फॉर लॉन्ग टर्म सस्टेनेबिलिटी ऑफ द फ्यूल साइकिल. दे आर पार्ट ऑफ इंडियाज एडवांस प्रोग्राम एंड दे ऑल्सो फीचर इन द लॉन्ग टर्म कैपेसिटी प्लान. But in SMR context, the practical engineering question becomes: should India scale down PHWR concept for SMR, या BWR या PWR? We have to adapt anyone. PHWR और PWR में main comparison क्या है? Why this comparison matters? One need to understand the point in simple engineering comparison. Main difference between PHWR and PWR from an operational and thermal hydraulic point of view is the operating pressure and temperature. In PHWR, operating pressure is around 100 bar and PWR it is 150 bar. So higher pressure in PWR gives a better subcooling margin. If I explain subcooling margin in simple language, it means that coolant remains stable liquid phase and is likely to approach boiling under rated power condition. So that improves thermal margin and supports stable heat transfer performance. Now there is another major difference which matters especially for non-DI deployment. PHWR involve online refueling, which means that plant has more continuous refueling requirement activity. It requires more routine operational involvement and more fuel handling infrastructure. Whereas PWRs generally have longer refueling intervals. So refueling happens in plant shutdown, not continuously. That means that operating cycle becomes more predictable and less operator intensive in day-to-day operation. That is one reason why PWR designs are considered more suitably for SMRs, especially for captive power or PSU-led deployments where simplicity and standardization matters a lot. India's current nuclear power status, where we stand today, we come to India's current nuclear status, where India has installed 25 nuclear power units and the installed nuclear capacity is about 8.88 gigawatt electrical, roughly 9 gigawatt. It is also mentioned that among these 4 are light water reactors. So India is not standing still. There is an active construction pipelines. Capacity under implementation is 13.6 gigawatt electrical, which includes 4 LWR units at Kudankulam, then 13 PHWR units and the PFBR. The point is India is actively building nuclear capacity. But if you compare 9 gigawatt electrical installed today and with 100 gigawatt targeted for 2047, it is clear we need multiple parallel pathways, strong execution capabilities, and this expansion program is, this you will find in any literature and in DIE website also. DIE 48 gigawatt and also in the parliamentary discussions, 48 gigawatt electrical already earmarked sites. For a significant part of future capacity, siting is not the major challenge because locations are already planned. The second fleet PHWRs at existing sites like Kakrapada, Naroda, Bhimpur in UP. This includes 4 PHWR totaling about 7 gigawatt. Beyond that, sites are available and DIE already has a plan already earmarked 48 gigawatt electrical. This 48 gigawatt includes major projects such as Jaitapur with 6 units of 1730 megawatt electrical each, then Kovada mein hai with 6 units of 1028 megawatt electrical, and then 2 fast breeder reactors of 500 megawatt electrical each at Kalpakkam. So 48 gigawatt electrical segment, the message is clear that this project site availability is already planned and located. So that's a strong foundation. But next question is, how do we move from this planned 48 gigawatt to the full 100 gigawatt mission? That is why PSU and captive deployment becomes important. Here, second big pathway are PSU and captive segment. Many other PSUs, even private sector companies, are willing to participate in nuclear power, and government is also exploring and collaboration. And presently, central government and central PSUs can own reactor, but after that, Santi will different era has already started. NTPC interest in working with NPCIL through a joint venture model, and capacity of 43 gigawatt has been kept for various PSU and state PSUs. So several reactor options are under this segment are BSR 220 megawatt electrical, then PHWR 700 megawatt electrical in a captive mode, then BSMR 200 and 300 megawatt, then SMRs 55, IPWR 700, then IPR 1000 megawatt. So why this 43 gigawatt segment important? Because it is expected that PSUs and industries can bring their own sites, and it has large metallurgical and heavy process industries. They have their own land and infrastructure already. Some have their already installed equipment, generator and turbines, all those installed, and those can be reused. The power requirement is very high, and they have the siting constraints may be reduced compared to conventional city link deployment. And from a national capability perspective, this creates a strong opportunity. If PSUs and industries participate, this can be scaled up and manufacturing improve execution speed and builds a strong domestic supply chain for nuclear grade equipment. So why SMRs are needed and captive power and data center ka demand kya hai? SMRs are extremely relevant in these new sectors. India has about 80 gigawatt captive electricity segment. About 90% of captive power is still fossil fuels. That means a major part of industrial electricity is produced from coal, gas or diesel. This causes high carbon emission, fuel supply dependence, cost uncertainty, long-term sustainability issues. So SMRs provide an option where industries can shift towards stable, low carbon captive power. For industries, this is not only a climate advantage, it is also a reliability and long-term cost stability advantage. Now, other major segment is data center. India has about 250 data center, while in the USA it is several thousand. So in the growth potential is very high. Data centers are energy hungry and highly sensitive to power quality. So SMRs are well aligned and with the need for continuous supply. Now finally, the direction is also aligned with reducing carbon footprint by 2070. This has already been declared by Prime Minister, and so SMRs also support long-term decarbonization goals without depending solely on intermittent sources, renewable sources. So the conclusion for this section is the SMRs are needed because they fit the future demand pattern, industrial, digital, stable and low carbon. ग्लोबल ट्रेंड देखेंगे तो वहाँ पे PWR का डोमिनेंस सबसे ज़्यादा है एंड SMR का डायरेक्शन इन एनी इंजीनियरिंग स्ट्रेटेजी ग्लोबल एक्सपीरियंस मैटर्स. सो we see that 70% of the global reactors are PWRs. That tells PWR is the most established commercial reactor platform worldwide. That USA fleet और example अगर देखेंगे 94 total reactors है, 63 are PWRs, 31 is BWRs. SMR में कौन सा reactor 10 से लेकर 300 megawatt electrical सारे IA definition में इसका यही दिया हुआ है. तो टू लीडिंग PWR-based SMR कॉन्सेप्ट जो है अभी मार्केट में ट्रेंडिंग है, वेस्टिंगहाउस का AP300, वोल्टेक SMR 300. दो ग्लोबल ट्रेंड शोज दैट SMRs आर नॉट बीइंग डेवलप्ड एज कंप्लीटली न्यू रिएक्टर टेक्नोलॉजी. यहाँ पे क्या है, ऑलरेडी जो प्रूवन टेक्नोलॉजी है उसी को यूज किया है एंड मॉड्यूलर बनाया गया है एंड स्टैंडर्ड्स को स्टैंडर्डाइज किया है. तो मेनली बिल्ड ऑन प्रूवन PWR फंडामेंटल्स बट इन स्मॉलर एंड मॉड्यूलर फॉर्म्स. सो इंडिया चूजिंग ए PWR-based SMR डायरेक्शन एंड इट इज अलाइंड विद ग्लोबल मेन स्ट्रीम रिएक्टर इंजीनियरिंग. BSMR क्या है, इट इज भारत स्मॉल मॉड्यूलर रिएक्टर. सो अर्लियर लाइट वाटर रिएक्टर डिपेंडेंस इन in India were mostly supported through imported designs. एक है तारापुर BWR जो सप्लाई किया था जी ने, then PWR unit supplied by Russia. BSMR is positioned as an indigenous specialized light water reactor direction. So important concept is that indigenous capability to provide long term benefits. इसमें क्या है, टेक्नोलॉजी ओनरशिप रहेगा inside the country, reduce dependence on external technology restriction and building domestic manufacturing of critical components. It is also noted that this national intent is to develop 5 indigenous SMRs. So this point has to be kept balanced, not about exaggeration. It is simply the fact that when India designs and builds its own SMR platform, it strengthens national self-reliance in high complexity engineering. This self-reliance benefits not only the nuclear sector, it uplifts domestic industry capabilities also, क्योंकि इसके साथ साथ सारे इंडस्ट्रीज आगे बढ़ता है, न्यूक्लियर ग्रेड स्टील, हेवी फोर्जिंग, प्रिसीजन पंप्स, मोटर्स, इंस्ट्रूमेंटेशन कंट्रोल, हाई क्वालिटी प्रोजेक्ट एग्जीक्यूशन, तो इसके साथ इतनी इंडस्ट्री में डिमांड आता है, एंड दोज इंडस्ट्रीज आर प्रोमिनेंट इन इंडिया एंड दैट विल ऑल्सो ग्रो जैसे न्यूक्लियर का प्रोग्रेस होता है. BSMR 200 का अगर डिजाइन की डिजाइन कॉन्सेप्ट देखेंगे, इट इज वेरी मच प्रैक्टिकल. वन ऑफ द स्ट्रॉन्गेस्ट आइडिया इज दैट रिटेन द सेकेंडरी सिस्टम्स एंड बैलेंस ऑफ द प्लांट. सो PHWR का दिस मीन्स वी रीयूज द प्रूवन सप्लाई चेन इक्विपमेंट बेस्ड फॉर स्टीम जनरेटर, स्टीम हेडर सिस्टम, टर्बाइन जनरेटर, कंडेंसर, HPP वाटर फ्रॉम इंजीनियरिंग एग्जीक्यूशन इक्विपमेंट. दिस इज वेरी स्मार्ट बिकॉज न्यूक्लियर आइलैंड needs careful design and qualification. It has to be proven one. If the conventional island remains familiar and proven, the overall projects becomes more manageable in cost and schedule. अगर PHWR के साथ कंपेयर करेंगे, PHWR 220 और BSMR 200 में क्या है, दोनों डिफरेंस क्या है? नो ऑनलाइन रिफ्यूलिंग, नो हेवी वाटर मॉडरेटर, रिड्यूस्ड ऑपरेटर इंटेंसिव टास्क, एनरिच्ड फ्यूल है, स्मॉलर फ्यूल फ्रंट एंड रिक्वायरमेंट, रिड्यूस स्पेन फ्यूल बर्डन, क्योंकि फ्यूल ही कम हो गया तो आपका स्पेन फ्यूल बर्डन भी रिड्यूस हो गया. सो रिफ्यूलिंग इंटरवल इज अराउंड 18 to 20 months, बट 24 months तक भी जा सकता है. इकोनॉमिकली इट इज एक्नॉलेज दैट फर्स्ट यूनिट जो है वो फर्स्ट ऑफ ए काइंड है, तो फर्स्ट ऑफ ए काइंड में कॉस्ट ज़्यादा आ सकता है, बट आफ्टर स्टैंडर्डाइजेशन एंड रिपीट कंस्ट्रक्शन कॉस्ट कैन रिड्यूस एंड अप्रोच एस्टेब्लिश वैल्यू. सो की मैसेज इज द BSMR 200 इज बीइंग डिजाइन फॉर रियल डिप्लॉयमेंट, नॉट जस्ट एज डेमोन्स्ट्रेशन. BSMR 200 का टेक्निकल पैरामीटर्स में कुछ बात करेंगे, इसके बारे में आपको डिफरेंट व्यूज मिलेंगे, बट जो लिटरेचर के हिसाब से अगर देखेंगे तो एक हो सकता है कि जो है इसका थर्मल कैपेसिटी, देन प्राइमरी कूलेंट प्रेशर अबाउट ऐसा ले सकते हैं 120 बार के आसपास, देन फ्यूल हो सकता है कि ऑक्साइड पैलेट्स ले सकता है, देन क्लैडिंग मटेरियल, देन बर्नेबल पॉइजन सेम रख सकते हैं, नो कंट्रोल जो पहले इसमें वो यूज होता था, देन रिएक्टिविटी मैनेजमेंट के लिए कंट्रोल रॉड्स, बोरिक एसिड सेम रख सकते हैं, देन कूलेंट इनलेट टेम्परेचर, देन आउटलेट टेम्परेचर, इसका डिजाइन जो होता है दोज आर ऑलरेडी, दीस थिंग्स आर रेडी. देन कोर एक्टिव हाइट, देन टोटल फ्यूल असेंबलीज, प्लांट कॉन्फ़िगरेशन क्या रहेगा, हाउ मेनी लूप्स आर देयर इन, तो यहाँ पे कितना लूप रखना है, देन स्टीम जनरेटर, रिएक्टर कूलेंट पंप क्या रहेगा, साइकिल लेंथ क्या रहेगा. सो दोज थिंग्स आर ऑलरेडी रेडी. एंड इवन फॉर नॉन न्यूक्लियर इंजीनियर व्हाट मीन्स द BSMR 200 डिजाइन यूजिंग मेन स्ट्रीम PWR इंजीनियरिंग अप्रोच विद अ बैलेंस प्रूवन एलिमेंट्स एंड न्यू इंडिजिनस डेवलपमेंट्स. सो हम प्रोग्रेस एंड रेडीनेस के बारे में फाइनली हम लोग देखेंगे. तो रिएक्टर फिजिक्स डिजाइन highlights that it's a stable PWR like behavior, enrichment up to below 4.5%. We can go and discharge burn up around 46 gigawatt day per ton. Initial boron concentration, negative reactivity coefficient across operating cycle. Negative coefficient means the reactor tends to manually naturally stabilize in many disturbances scenario in an important safety and stability feature. So engineering readiness में ये part भी आता है. Then reactor pressure vessel is the most critical lifetime component. It must survive decades of high pressure, high temperature and neutron radiation. So design requirement इसका भी है, and that also in line with the ASME section 3. Then major indigenous process में जो है उसमें आता है अपूर्वा ग्रेड लो एलॉय स्टील फोर्जिंग, सो हेवी फोर्जिंग कैपेबिलिटी, इसमें भी हमारा सेल्फ रिलायंस की तरफ हम लोग आगे बढ़ रहे हैं. देन रिएक्टर कूलेंट पंप, इसका भी डिफरेंट पैरामीटर्स होता है, इसका हेड, देन RPM, देन कितना मेगावाट का हो सकता है, कितना वोल्टेज का, प्रेशर बाउंड्री मार्जिन कितना है. देन फ्रॉम इंजीनियरिंग पीपल दिस क्लियरली शोज द इंडस्ट्रियल ग्रेड कॉम्प्लेक्सिटी, हाई रिलायबिलिटी रोटेटिंग इक्विपमेंट ऑपरेटिंग एट एक्सट्रीम कंडीशन. देन कंट्रोल लोड मैकेनिज्म जो है मैग्नेटिक जैक कंट्रोल, अगर देखेंगे सेफ्टी क्रिटिकल शटडाउन एंड कंट्रोल इक्विपमेंट है. सो मोस्ट इंपॉर्टेंट फीचर है कि ये फेल से बिहेवियर, अगर पावर फेलियर है तो कॉइल्स डीएनर्जाइज हो जाएगा, रॉड्स विल बी इंसर्टेड बाय ग्रेविटी ड्रॉप ओनली, तो रिएक्टर शटडाउन. सो डिजाइन इज फेल सेफ. एंड इसका अगर रेडीनेस देखेंगे तो फिजिक्स डिजाइन, इंडिजिनस मटेरियल डेवलपमेंट, पंप ड्राइव मैकेनिज्म एंड एग्जीक्यूशन स्ट्रेटेजी, सो दैट प्रूव्स दैट सप्लाई चेन वेयर पॉसिबल. So I'll be concluding now. India's nuclear expansion mission is large and the roadmap includes both large reactor projects and SMR deployment. DIE has already planned sites for around 48 gigawatt and proposed PSU. So SMRs are needed because they match the new demand landscape, captive industrial power, digital infrastructure like data center, along with long-term decarbonization objectives. BSMR represents India's indigenous direction in PWR-based SMRs aligned with the global mainstream technology and national engineering self-reliance. So importantly, progress is not only conceptual, it is a key concept like reactor pressure vessel, steel, coolant pump, control rod, drive mechanism and many other engineering aspects. थैंक यू. एनी क्वेश्चन रहेगा तो चैट में डालिए.